Hello and welcome to the third lecture of Machine Learning for Robotics and Computer Vision. In this lecture we will talk mainly about classification models. But first let's start with a short recap of what happened in the last lecture. In the last lecture we talked mainly about regression and the linear regression specifically and the different variants of this. And we derived rules for learning linear regression for the maximum likelihood estimate, but also for the maximum a posteriori estimate, and also covered the Bayesian estimation, where we got the thing on the right, where we also have uncertainties for all our estimates that we do in the end. And the special thing here was that we could derive learning rules which were given in a closed form, so that we can just put in all the numbers and get the estimate out in the end without doing something in between. So the thing that we covered in the end was the discriminative and the generative model, and talked a little bit about the differences between these. But in this lecture we will cover classification, and here the target is not anymore a continuous value but a discrete value. So for each feature vector we want to estimate a specific class or label, like shown here. So on the left side we see the feature vectors, on the right side discrete labels. And in the lecture we will use usually this representation here. So we visualize the feature space, and in difference to the regression we don't have anymore the target value on the y-axis, but we have here now the second feature value. So that means one point like this here, the 0.9 and 0.2 corresponds to some point in the feature space, and we symbolize the label by coloring this point like this here for class 2, like green points. And the task that we are interested in now is to learn some model that gives out a probability P of y, which is now P of y given x, which is now a probability distribution. So we get for each of the different classes a probability. And with this equipped we can then hopefully derive also the class for unknown examples. So examples that we've not seen in the training set before. And this is now the main topic of this lecture, to derive classification models that achieve this, that we have an unseen point like this here and can then say in the end confidently which class it has. But as promised in the last part of the last lecture, we will also cover now here a generative model. So just to remind you what was the difference between a generative and a discriminative model. So in a discriminative model we are directly modeling P of y given x. This is also the thing that we are usually interested in. But using Bayes' rule we can reformulate it such that we have here P of x given y times P of y divided by P of x, just usual Bayes' rule. So that means we can also get in the end P of y given x by just modeling P of x given y and P of y. Or we can equally, by using also like the joint probability here and the conditional rules, also the joint probability over P of x and y. So yeah, and we will now talk about a specific generative model for classification. And in this case a very simple generative model is the naive Bayes model. In the naive Bayes we make a specific assumption on the feature distribution, so on the distribution of P of x given y, and we make the assumption that all the features are independent. And by this independence assumption we can write this joint probability over P of x as a product of probabilities for each feature, for each individual feature. So you will note that here is a bold x and here is a non-bold x, so this is really one specific scalar. So, and the model assumptions that we are now doing here for the derivation is that we model the distribution over the features as normal distribution. So we have for each feature xd a mean value and a variance. And for the P of y, we are just assuming that we have a categorical distribution. So that means we get out a lambda k for each class, and we ensure that the lambdas sum up to 1, so that we have in the end a valid probability distribution. Equipped with this, we can now derive the learning rules, how to estimate the parameters like the mu and the variance of the normal distribution, but also the values of the categorical distribution. And for this, we are deriving here mainly the maximum likelihood estimate, but of course, you can also do the maximum a posteriori estimate, and the Bayesian estimation is also possible here. And as you might have noticed from last time, the usual recipe to do this is by first deriving the negative likelihood term, then using the gradient of the negative likelihood to find the parameters by setting this then to 0. So determine the parameters where the gradient is then in the end 0. So in this recipe we will now use all over the time to derive in the end the learning rule for the specific models. And when we come now to the naive Bayes, then we start again with the maximum likelihood of the parameters, which is then given just the parameters theta star that maximize this likelihood of the parameters given the labels and the features. And we can then rewrite this as, because we have the assumption, the independence assumption of the training examples, as the product over all the probabilities of the likelihoods. So, and when we then use the naive Bayes assumptions, we can then just replace these P of y given x by the P of x given y times P of y. And with the naive Bayes assumption, we are just having the product here over the P of x given y. And with this, we can then go on and use the usual trick, the negative log transform, which ensures that with the logarithm, we're ensuring that we get in the end the same maximum out, even if we use the logarithm in before, and with the negative log likelihood, we want to have a minimization in the end. So therefore, the maximum changes here to the minimum, and we're just putting in front of it a minus log. And the good thing about the logarithm, as I said in the last lecture, is basically that we can then replace the products when we push in the logarithm with sums. And then we have the, here is also a product, so we have the sum over the log probability of the feature and the log probability of the classes. And this is then, as usual, our negative log likelihood term. And when we now want to determine the parameters for P of x given y, we can just concentrate here now on the part that is really relevant for this, because the y's are not relevant for this, and therefore we are dropping a lot of terms here. So because of the independence assumption of the features, we can just concentrate on this term. This term is not relevant because the parameters don't depend on these parameters here from the P of y. And yeah, we are just using here some shortcut to speed up a little bit the derivation. So, and when we then plug in our assumption that P of x given y is a normal distribution with these parameters, so with this mu and with this a variance of sigma square, then we can also now make the specific case that we are only interested on the features for a specific label, and therefore we are now assuming here P of y equals k. And by using this, we are now replacing here the n that goes over all examples with just the number of examples that are having the class k. So this is denoted by n and k. And then we just plug in the normal distribution equation, and then, yeah, we just push in the logarithm again. And then by using this, we're getting then this terms out, and this is then used to derive the gradient. And for the gradient, we have now to have two parts. Basically, we first determine the gradient for the mu's. And with this, we can then write it as follows. So this is just a copy from before. We are now deriving with respect to mu d, so for the specific feature. And as you might know from calculus, these terms are just constants, so they go away. And then when we have the squared term, then the 2 goes in front, so this vanishes, and then we are just left with this term here. And the thing that we can now do is basically to push in the sum, so that we have the constant out of the bracket here, and can rewrite this sum over xd minus mu d as the sum over all xd's minus the sum over all mu d's. And of course, when we just sum up over nk times basically over the mu's, then we can just write this equally as nk times mu d. And yeah, then comes the thing that we all also did with the linear regression, is that we now have the gradient and we are looking for the minimum, and the minimum has the requirement that there the gradient is 0. So we set this to 0, and then by just doing some algorithmic transformations, we get in the end out that the mu is basically just the mean over all feature values, which should be not so surprising because we have specifically here assumed a normal distribution. So this is now our maximum likelihood estimate for mu, and the same thing we are just doing for the variance. So, and yeah, I shortened this a little bit, so I just took the equation and then plugged in the logarithm of everything. This is then what is in the end coming out, and then we setting this to 0, and then when we set this to 0, we are getting basically out that the variance is basically the variance over the feature values. And so that the maximum likelihood parameters are in the end the mean over all features and the variance over the features, which is basically the thing with the normal distribution. So nothing very surprising here, but this is now the derivation for this. So for p of y, I'm skipping now a little bit of the derivation because it's a little bit, because we have this constraint here. So there we are using the Lagrange multipliers to ensure that the lambda k sum up to 1. And then when you do all the transformations there, then you come up in the end that the lambda k is just basically the number of all examples that have this specific class divided by the number of all classes, or all examples basically in the end. And that makes also sense for the maximum likelihood estimate, because when we then now think about this, when we have now the derivation of the parameters and we have now the normal distribution over for each feature, we can think about the naive Bayes that it gives us in the end something like this. So for the p of x given y, now for y equals 1 and for y equals 2, in this example here, we get for each feature basically a normal distribution that tells us where are the most likely parameters for this specific class. And in this case, for x1, the parameters should lie here in this range to be the most likely in the end. And we can do this also for the others. And so we see basically this gives us somehow ranges over the features where we expect that the an example that corresponds to this y equals 1 should lie in the end. But of course, the naive Bayes is not really always fitting, because there is no free lunch. So that means not this model and the assumption of these models will not always fit to our problem. And therefore the limitations are here, of course, that we only can have per feature a single range, so to say, which is the thing that we assumed in the beginning, that we have a normal distribution, and the normal distribution can only have one peak and a specific variance. So that means we cannot have maybe two peaks here, so that whatever for x3 is maybe here, some parameters that are very likely, but also in the bottom part, for instance. And we made, of course, a very strong assumption that we assumed that the features are independent, which is, of course, not always the case. For instance, for images, it's not reasonable to assume that neighboring pixels are independent from each other, because we are maybe capturing the same object, and then on the object, of course, the pixels nearby have some relation to each other. So, and therefore, now we are looking for a model that is maybe more powerful in the end, and for this we are just covering here a very simple model, but which enables us to have multiple ranges per features. And this model we are talking now about is the decision tree. And in the decision tree, the idea is to build a tree where we have the inner nodes of the tree such that they have split functions which decide where to go in the tree. And the leaves basically model then the p of y given x, but only for a subset of points. The split functions are built such that they return 0 or 1, so deciding where to go in this tree. And we are now covering what are the ingredients of a decision tree, but also how to learn a decision tree in the end. So as I said, the split functions decide where to go in the tree. And a very simple split function is basically that we are just using some feature, so xd, from the whole feature vector, and then just threshold it with this tau here. So that means if xd is smaller than tau, then we are returning 0. And when xd is greater or equal to tau, then we are just returning 1. But of course, we can also use more complex functions. But this is already, when we combine it and make a very deep tree, a very capable thing in the end. For building the decision tree, we can now use the following receipt. So we have this create node functions, which gets a set of examples and a specific depth. And when we decide to build a specific depth of the decision tree, we just stop at the maximum depth and then return a leaf, which is then the probability distribution over the set that is put in here into this function. So that means for this we are just using the categorical distribution that we had also with the naive Bayes, so that we just count how many examples have a specific class and divide this by the number of the examples that are left at this node, basically. And then when we are not building a leaf, we have to decide on a split function. And then we are splitting basically with the split function. So this is something that we discuss in the upcoming slides, how to find a good split function. But let's assume that we have now found a good split function. Then we are just splitting the set that we get into two subsets. So basically a set that goes into the left branch and a set that goes into the right branch. And it's such that we take all the examples from the S that have the split function equals to 0, and we put it in SL, and then in SR go all examples that get from the split function a 1 returned. And with this, we are then building some inner node with the specific split functions, so that when we later use a different X, we can still decide where to go. And then we just call recursively the build function again. But now the important part is that the create node is now getting the SL and the SR, and we increase the depth by 1. And then the recursion happens, so when we reach the maximum depth, we are creating a leaf again, and when it's not the maximum depth, then we are just doing the split again and then going on and on. So, and with this, we are getting then in the end a decision tree that hopefully models our distributions such well that we get out a good probability distribution in the end. But now the question, of course, is how do we get a good split function? And for this, we have to dive a little bit into some theory, but it's nothing very complicated in the end. So what we want to achieve in the end, or what we want to measure is basically the information of the subset. And for this, we have the concept of entropy. So the entropy provides basically a measure of the information in this set. So, and here we are reasoning basically about the class distribution. So for the set S, we are just determining the probability that P of y equals k, which is just basically the categorical distribution derivation. So we just count how many of the y's equals to k and divide it by the whole number of all elements in sigma, and as shown here. So when we use this specific definition, we then get out the entropy. And as you will see now in this example, so the entropy encodes somehow how much information is in this set encoded. So when we have such a distribution, so that the equal distribution, then the entropy is very large. So we have very few information basically inside this subset. So, and when we use the logarithm of 2, so this is a specific thing here we are just assuming for to make it valid in the end, that the logarithm of 0 is just equating to 0. But when we use this definition, we then get out the entropy here, and when we use the logarithm to the power of 2, then we get also out the bits that are needed basically to encode this set. So with these three examples basically here, we need basically 2 bits to encode all the 3 examples, at least. And when we now look at a more peak distribution, then we will see that the entropy is shrinking. So the information inside this set is much higher, because you can think of it like whatever, you have a bag, and in this case you have a bag of whatever number of balls with different colors, and when you then pick balls out of this bag, then after a time you will not know what is the most likely thing that you can get out there. But when you have this bag with this distribution, then you will figure out after a time that it's more likely to get the yellow balls out instead of the green. Therefore, the entropy is lower in this case. And in the specific case of the decision tree, what we want to achieve is in the end such a distribution of the subsets in the end. And so the split function should give us subsets such that the entropy is lower for the subsets. And how to measure this, the gain that we get by the split function in terms of entropy is called the information gain. And the information gain is then defined as over the sets S, SL, and SR, such that we have the entropy of the whole set, and then subtract the entropy of the subsets, and we scale it by the number of items in the subsets. And with the information gain determines how the entropy changes between the original set S and the subset SLs and SR of this set. So, and with this we can now determine split functions that maximize the information gain. And here's just a little example. So we have these points here with the specific classes, and then we have maybe the 3 split functions here. And for each split function, we can now determine the information gain. I just repeated here the equation that we had before. So, and for all the split functions that for the derivation that comes now, we need essentially the entropy of the whole set. And as you can see here, when you count them, then we have 3 items of the blue ones. They are in overall 10 points, so we have 0.3 as probability for blue. And then for yellow we have 4 points, so 0.4, and for the green points we have 3 points, so that means 0.3 again. And this is roughly basically the uniform distribution that we had before. And as we saw, we had there a value of 1.8, 1.58 or something like this, and here's now 1.57. So the entropy is it's essentially the same as for the uniform distribution. So, but when we now look at the different splits, we can then determine the information gain. So as I said here, the entropy is always the same, so we can plug this in here. So, and for the left subset, we have now two examples basically in there. So the, the scaling factor is basically 2 divided by 10. And because we have here again a subset now with 2 examples, the entropy will turn out to be 1 in this case. Because, yeah, that's the maximum entropy that we can have for these 2 examples. And the rest of the set are then the remaining 8 points, and this will give us then an entropy of 1.56. And when we then do the arithmetic, then we get out that this split gets an information gain of 0.122. So, and as we will now see, when we take a different split, we get out a different information gain in the end. In this case, we have here now the set on the left side has again 3 points that are from the blue class and 3 points from the yellow class. So not so surprising, the entropy is the same as before because we have just the same distribution there. But now, as you can see here, the entropy basically of the right set is largely decreased because we have here now only 4 points, and its 4 points have 3 green points and 1 yellow point, and therefore the distribution basically over the P of y's is basically more peaked, and therefore the entropy here is decreased. And then you do the arithmetic again, and you get 0.64 in the end. And for the third split, it looks now like this. So for the left part, yeah, the entropy is not so much reduced, but as you can see, as we have now here only 1 class inside there, the entropy is basically 0. So because when you have only maybe green balls in your bag, you don't need to use any bit to encode it, for instance. Therefore, the 0 makes sense there. So and as you now see, maybe between these 2 cases, we had the first case where we had the split here, and the case that we had the split here. So the difference here is quite significant. So, and this is also the thing that basically the split functions want to achieve in the end, to have as pure subsets in SL as possible. So that means only classes of one specific kind in the subsets, and this is what then is basically maximized in the decision tree in the end. When we then use this, for instance, with the simple split functions, we can then determine, for instance, all possible splits per feature. This is then this set HS, which just encodes all split functions for all the features and all the possible tau values, where we just use the feature values basically as threshold. And yeah, this is, we just search exhaustively for all the possible split functions in our subsets, but we can also, when we have a larger training sets, to speed it up a little bit, we just can use a fixed number of splits, so that maybe we determine the minimum and maximum in this dimension, and then just take 10 splits that are equally distributed over the whole continuum, and then use this as split functions. But this is something that you can decide in the end. And when you then have used the build function, it basically determined always the split function with the largest information gain and split your set, you might be getting then out something like this, so that you have the decision tree, and each node now induces some split in the feature space. And then when we have now a new point that we want to have the label in the end, we just walk down the tree from the root we are starting. With this split, we can see then that we have to go basically on the right side, and we are using then here the next node. We are then just using here the split again, and then we see that we are on the left side of this, and then we are passing down the tree until we reach a leaf. And when we are in a leaf, we can determine the probability distribution over all the examples that were in reaching the leaf in the training, and then assign here, for instance, the class green for this point. And so the decision tree is basically not so complicated, but in the next lecture we will see how we can maybe use this decision tree to our advantage. But for now, this is an extension of what we had before, because before we had only the possibility to encode basically one range of values, and now because of the splits we can basically split up each feature dimension basically here in multiple ranges where we're expecting the test examples, for instance. And as you can see here, each split function in the nodes induces some decision boundaries. So that means at these decision boundaries, the class will change from one class to another. And this is usually something that you will also see when you talk about classification models, that you have the decision boundaries, which tells you where the class changes in the end. And the question is now, okay, here we had now somehow implicit decision boundaries, but maybe there's a possibility to directly learn the decision boundary between the classes. And this is this thing that I want to cover now. So how to learn directly the decision boundaries. When we look at the geometric representation here, then we have maybe two classes, the blue class and the red class, and then we have the decision boundary between these classes. And the decision boundary is basically a hyperplane. And in this case here, a line, which is then encoded by theta transpose times x plus theta 0. So it's just a linear relationship here, and as you might remember from the Hessian normal form, so when this theta is normalized, then this will give you out basically the distance of each point, the Euclidean distance of each point to this plane basically. But in this case, because theta is not normalized in the end, this will be somehow then a scaled distance. But using this distance concept, we want now to convert basically the distance that we get out from this into a probability distribution. And such that whatever points that are far away get a higher probability for this class here, so for this red class. So when we are going in this direction, we have a positive distance, and the more positive it gets, the higher the probability for this class should be. And when we have this decision boundary and then go in the negative direction, then the probability should go to 0, that this specific class is attained in the end. So, and the thing is now, how do we convert basically this continuous values, which can range from -infinity to infinity, into something that goes only from 0 to 1. And there's something specific that we can use here, that's the so-called sigmoid function, which allows exactly to do this. So we put in a value, a real value from -infinity to infinity, and we get out a value that ranges from 0 to 1. And the sigmoid function is defined by 1 over 1 plus the exponential of -x. And when we plot this, then we can see here that for negative values it approaches 0, and for the positive values it approaches 1. And the good thing here is basically that when we think again of the distances, so the distances from the hyperplane, when they increase, then the probability increases to 1, and when the distance decreases, the probability decreases to 0, so to say. And the good thing is here, one specific thing, that at 0, when we are exactly basically on the decision boundary, then the sigmoid function handily puts out 0.5, which is also a good thing in the end. When we now use this geometric view of the decision boundary together with the sigmoid function, we get for the binary classification something out that's called logistic regression. So for the binary classification, we want to achieve basically that p of 0 equals 1 minus p of y equals 1. And for the logistic regression, we are just using our intuitive model from before, that we model here the decision boundary and we pass it through the sigmoid, which gives us then the probability for p of y equals 1 given x. When we plug in this, then we get basically the fraction here, 1 over 1 plus exponential of minus theta transpose times x. And as before, for the class 0, we are just assuming that it's 1 minus p of y equals 1. And yeah, you might remember from the linear regression part in the second lecture that we used the trick that we included the bias by prepending basically the 1 in the beginning. And therefore we can now include the theta 0 that we had before just in this term here. And this makes the notation a little bit easier in the end. And now, yeah, to learn this model, so we want to determine the thetas that achieve exactly what we want in the end, so that the decision boundary lies between two classes, and that the probability of one class when the distance increases to the decision boundary gets larger and so on. This follows again the usual receipt. So we are having now our model, our probability distribution for p of y equals 1 and p of y equals 2, p of y equals 0. Usually we want to determine the maximum likelihood estimate here, so we derive first the negative log likelihood. So we plug in the values again. Here, in this case, we have the logarithm over the product. So for the maximum likelihood, then we put the logarithm in so that we have the sum again. Everything as before. So here we make a notational thing that we distinguish between the probability basically when the label of this example is equals to 0. So that means we have here this indicator function which just returns 1 when the argument is true. So in this case, when the label of the east example is 0, then this returns 1. And then we want to use basically this probability. And then we just do the same for the other class, so that we want now the probability here for p of y equals 1. It's just a notational thing in the end. And now I don't want to bother you with the derivation, but you can find it, of course, in the lecture notes, the whole thing, how you derive it in the end. And then when you change the terms a little bit, then you can write out something like this, so that you have then the indicator function saying that the east label is 1 minus 1. This in brackets times the distance, so to say, and minus the logarithm of this. And this is then a negative log likelihood of the logistic regression. And then, as usually, we derive then the gradient again. So nothing very complicated here. So we have the equation from before, the negative log likelihood. Then we derive according to theta. So as you can see here in this first term, the theta is just a linear term, so it will be dropped. Here with the logarithm, it gets a little bit more complicated, but also nothing very surprising here. So we use just the chain rule. So the logarithm is 1 divided by the x value basically. Then we have the inner part, which turns out to be this. And then we have the part that is left here, which is basically then just minus x. And when we see this, basically we can use this fraction here, and when you do the derivation in the end, you can replace this basically by 1 minus sigma, which is basically then 1 minus sigma of this theta transpose x. We can place this in here, then whatever, put the x out of the bracket, and then we have the sigma here. And with this, we are then just having here this equation in the end. And when you remember how the probability was determined in the beginning or defined, then it turns out that this sigmoid of theta transpose x is basically just our definition of p of y equals 1. So, and when you now look at the gradient basically, then you see basically why it makes sense to have it in the end. So then the p of y equals 1 is very large, so it approaches 1. So and it's correct basically. Then the real label is also p of y equals 1. Then this term will vanish. So that means in this specific case, the gradient will not have any influence there. So because this is already correct. But if the p of y is not 1 in this case, then we move the gradient basically in the direction such that the distance is basically increased. And the same happens, of course, for the p of y equals 0. So when the class is 0 in this case, then we move basically the theta value basically in the direction such that we decrease the distance. So and this is so the intuitive thing. So but the problem here is now with this term we cannot find a closed form solution in the end. So we can set this to 0 and try whatever what we want. There's no real closed form solution for this. And when we don't have a closed form solution, then how do we determine basically this theta in the end? And this is then something where the optimization part of machine learning comes in. So when we have the gradient, we can basically then use optimization methods to go in the directions where the theta is minimized or the non-negative log likelihood is minimized. So we might have such a function, which is here now this red function, and the whole idea of gradient descent is basically to determine at the last parameter value the gradient, and then use the gradient to go in the direction where the minimum should lie, because we are going just downhill basically here. And therefore the update rule for the gradient descent is basically that we take our last parameters, evaluate the gradient at the last parameter values basically, and then subtract this from our parameters. And what specifically, because we basically, because how the gradient works is basically it is only looking at a small part basically of the function. So we don't know how it changes after this. So because as you can see here, the gradient is going in this direction, but right after that is going down much more. So therefore, not to miss basically the minimum, we are scaling just the gradient by a term that is called the learning rate. And we want to choose the learning rate such that it's not whatever overstepping or going in the wrong direction basically in the end. So, but I think this gradient descent idea, I think, should be also already known from the other courses. So the thing now with the learning rate is that the learning rate, of course, influences how quickly we approach the minimum in the end. So, and the thing is here, when we choose the learning rate basically too small, then we will, for instance, here in this plateau, make only small increments to our theta value, so that we can, not as fast as we might want to have in the end, reach the minimum here in the end. But on the other side, when we make the learning rate too large, then we maybe have this thing here. So we are making now a larger step, but because here the gradient is very steep, we are doing here in an even larger step, go over in this direction, and then we determine here the gradient at this position. And here, as you see in this function, the gradient is also very steep in the end. So we are doing, again, a larger step in the other direction. So therefore, you somehow have to find a balance between not being too small, but also not being too large. While being too small is usually not a big problem, it just takes longer to optimize. Anyway, so finding the right learning rate is somehow a tricky part, and especially when you have models with many parameters. the solution that you can use basically in these models, for instance, for logistic regression, is that you also determine the Hessian, which is the second order derivative, and scale then basically your gradient update with the inverse of the Hessian. But later we will also see some examples of first order optimizers, so like gradient descent, that do a better job than using the Hessian basically. Or not a better job, but also a good job without using the Hessian. So, and now coming back to the logistic regression, so we now have the gradient derived, we now know how to optimize basically the parameters such that we find the maximum likelihood estimate or the minimum of the negative log likelihood. And when we apply this, then we somehow initialize this theta with some random values. In this case, I choose here these values. And then we see here, okay, just a short explanation what we're seeing here. So on the left side, you basically see our training data set. And you see this theta that is currently the decision boundary that we estimated. And based on this theta, we are also coloring the each point in the feature space basically by the probability, by the probability P of y given x. So, and you will see here reddish colors when P of y equals to 1 is large, so for the red class it's large, and blue colors when the probability for the blue class is basically large. And in between you see the gradient basically between these two classes, or the two red and blue values when the distribution changes. So it's just a mixture of basically this blue and this red in the end. And here in the middle you see the negative log likelihood estimated at the current parameter values, and this is in the case when we start with this, it's something like 15.2. This will then also evolve. And then here on the right side, I also plotted basically the length of the gradient, which is then telling you how much you go in this direction basically. And when we update now with the first step, we see that the negative log likelihood is decreasing, which is a good thing for our gradient descent optimizer, and the gradient is also decreasing. So we are going down here. So, but the most important part, or the part that you're mostly interested in, is basically the loss curve or the negative log likelihood curve that should go down and reach somehow a minimum in the end. And when you do this third iteration, you also already see that also the decision boundary is changing in such a way that most of the examples are now on the right side basically. And the blue examples on the other side. And when we update this again, you will see here some wiggling, so fixing the parameters, but you also see that the negative log likelihood goes down. And when we do this furthermore and furthermore, we see that the decision boundary is now reaching a state where it's maybe, in this case, optimal, separating the examples in the end. And when we do this further, here's just the visualization, then you see that the decision boundary is fixed at some point, and then the negative log likelihood is still decreasing, so we're updating just more. And what you can see here is also that now comes this part in, so the theta is already in the right direction, and at least in this example where we have linearly separable examples, we can then increase basically the theta as much as we want, because this is something what we want to achieve in the end. For the examples where the label is already correct, we want to push it as much as possible to 1 for the one class and to 0 for the other class, and this for P of y equals 1 and so on, P of y equals 0. So, and here you also see that the gradient is also decreasing. So, and this is now done for 100 iterations. So This is then something that we reach after 100 iterations. So we have a decision boundary found that separates these training examples, and the probability distribution assigns basically large values to the red class when it's on the positive side, and large values to the blue class when it's on the other side, so to say. And in between you see that it's decreasing, which is basically also coming from the sigmoid function, so that at the decision boundary basically it's 0.5, so you get the mixture of both colors in the end, and then you have this decreasing part here. And now you have to somehow decide when to stop this optimization, and usually one can say, okay, we just use a fixed number of iterations, so we maybe looked at the curve, and we decided, okay, we stop just after 50 iterations, so this is also called early stopping, so to say. But we can also look at the gradient. When the gradient is nearly 0, then we are sure that we reached basically a minimum, which is not necessarily the global minimum, but maybe a local minimum. Or we can just look at the objective function, in this case the negative log likelihood, when this changes not so much. Usually it's something in between, so you have multiple criteria in the end. Yeah. Of course, we can also extend this to multiple classes, and there we follow the same idea. So basically, for now we have for each class basically a theta, and we want to find the theta such that whatever the distance to this theta or this induced plane is basically as for the correct class as large as possible for this plane. So hopefully it will be clearer when you see the example. So the basic thing, so the difference now to the logistic regression is basically that we have now a theta parameter for each class. So in this case we have a 3-class problem, so we have basically 3 thetas in the end. And by then using the same idea, so that the distance to this plane basically should encounter the probability, we have to now figure out a way how to use this to our advantage. So to say, we want to have that the largest distance basically to term theta should have also the highest confidence in the end. So, and we want to find a parameter such that the distance is maximized for the correct class, so to say. And we have now to turn these multiple distances, so the distance for this point, basically in relation to this plane and to this plane and to this plane. So in this example, the red point should have a large distance to the red plane. So by scaling the theta or something like this. And here in this case, for instance, it has a negative distance, which is good, and here also a negative distance, so here it would be fine in the end. But we want to turn basically these distances also in some values that make sense in the end. So how do you turn the distances that you are calculating by using this x transpose theta or theta transpose x? So I changed this in between. So how to turn these distances into a probability distribution. And there comes another function into play. So, and this is also something that is usually used, is the softmax function. So, and the softmax function does the following. So you put in a vector of real values, and it will turn this into a vector of values that are between 0 and 1. And now the special thing is here that they sum up to 1. And the softmax function is now defined like this, so that you have the exponential of xi divided by the sum over all entries of x. So, and therefore this is really returning a vector with values. And these individual values are encoded like this. It's always like the exponential of this, the ith value divided by the sum. And by using this, we then have the properties that each Si is in the range between 0 and 1, and the sum overall is also 1. So this is something that we want to have for probability distribution. And now some examples for the softmax. So here we see when we put in the same values, that can be arbitrary, but when they're the same, then we get out this what we want in the end, that the values are 1/3, 1/3, 1/3. So an interesting part is now what happens if one of the values is larger than the other values. And the softmax is then returning a larger value for this. And this depends on the difference between the individual values. So it doesn't matter if it's whatever 1000 and 1001 and 1000. It will turn out to be similar to this. And it just encodes basically that this is the largest value. And as you can see, therefore it's also called softmax. It's the soft representation basically of the maximum, or the argmax in the end. When you would now use this value, you could find out that this was the largest value in the end. When you now have a more extreme example, extreme in this case that the distance to the other the other entries is larger, then this will also increase here this value in this case. And for the other values, because they are the same, it's also putting out the same numbers in the end. And when we do this now for a more complicated example, then you will also see that the smallest value from these values that we put in gets the lowest value in between 0 and 1. And the largest value gets the largest value. And it's also guaranteed that they sum up to 1 in the end. And using this idea, we can now define our multi-class logistic regression. In the following, I will just call it Softmax regression, where we just say that the probability distribution over all classes is just given by the softmax over the thetas for each class times the x. And for an individual class, then it turns out this is just the definition of one entry of the softmax, which is then the exponential of theta t times x divided by the sum over all classes. Unfortunate, here is also the case that when we do the nonlinear log likelihood of this thing and determine the gradient, then this will also not turn out to be a closed form solution. Just shortly to derive this, we just start again with the nonlinear log likelihood, the negative log likelihood, sorry. Then, as you can see, the usual thing, we plug in our model, then use the logarithm. So the good thing is here that the logarithm cancels out the exponential, and in the lower part we are just keeping the sum here. And what I did here is basically I pushed in the minus, so therefore the terms are changing here in this specific case. And one thing to note here, when this is not theta but some x's, or this is the sum over x's, then this is also called cross entropy loss in the end. So this term is basically the cross entropy. And when we now want to derive the gradients, we derive the gradients basically for only a single class again, because it's a little bit simpler. We have here the nonlinear log likelihood, the negative log likelihood again, and we derive it in respect to theta j. So that means we have to make the derivative of this. That's again the logarithm is 1 divided by the term that it's inside the logarithm. In these terms, in this sum basically, of course, because we are just deriving or have the partial derivative respect to theta j, we are left with the theta j here in this case. And the same when we have just the theta j, in the end it only remains the xi. And on the right side we can use again the indicator function to make it a little bit shorter, because here from the thetas we are only interested in the thetas when they are basically for the class j basically, and therefore we are just saying that if the the class of the example is j, basically, we want to have this term in the end. If it's not j, then we just drop it. So this will turn then out to be 0, and then this cancels out in the end. And when you then put this xi out again, and then you have the exponential goes up on the fraction, then you will see here that we have again just the softmax, and this is exactly the definition of the probability for class j minus if this example has the class j. And as in the logistic regression, so that's exactly the same. When the class is already the same, so it's already 1 basically for the correct class, then we will have no gradient influence there basically. And if it's not j, we have to push it in the other direction basically, and therefore it will have the influence like the influence with the probability that we are currently assigning. So it makes totally sense in the end. And when we come to the example again, again here we have now 3 classes, so you will see a mixture of all colors here, so blue, red, and yellow. We have in the middle the non-negative, the negative log likelihood again, and on the right side the length of the gradient. And when we run the optimization again with gradient descent, so we use the gradient again and then plug this in, and then we see the following. As you can see, the solution is converging now to something that the yellow points are basically in this region where only yellow is predicted, and the red points are in this the region where only red is predicted, and so on. So, but the interesting thing to note here is that the thing that we had for the logistic regression, such that the thetas correspond basically also to the decision boundaries, is not necessarily true anymore. Because you see here the theta for the yellow part is basically now here, and for the red class it's here, and for the blue part it's here. So which is not basically the decision boundaries we are usually seeing here. So and when we have this example here, in this case, decision boundaries would be something like here. So this is something you have to note or keep in mind, so that the thetas are not necessarily anymore the decision boundaries between the examples. And yeah, with the logistic regression, we can also do, of course, the other stuff that we also did with the linear regression. So basically, we can make the estimates less overconfident in the end. So what I described, so that when you optimize long enough, then basically the probability on one side or on the other side will be whatever, just 0 or 1 in the end. And this can be avoided by using the regularization term. So then we have the maximum a posteriori estimate. And usually the thing that one does is, again, just use the L2 norm. So it was like theta transpose times theta as additional term in the negative log likelihood, and then it turns out to be just the same gradients in the end. But we can also make the logistic regression nonlinear again by using the nonlinear transform on the features. But we can also use the Bayesian logistic regression. But the thing now, as you saw already for the maximum likelihood, this is also true for the Bayesian estimate, that there is no closed form solution. So you have to do something to get it out in the end. But for this, you can look also in Prince's book, the Computer Vision Models, Learning and Inference book. There is everything also described, so if you're interested in this. And with this, I'm also coming now to an end. So in this lecture, we basically looked at classification models. So we looked at the naive Bayes, which was a generative model, then the decision tree, and in the end, the logistic or the softmax regression. Which both, so the decision tree and the logistic and the softmax regression were, of course, discriminative models, because we directly model P of y given x. And we also touched basically a bit the optimization with gradient descent, but the optimization part will play later also more important role. Yeah, with this, thank you for your attention, and see you next week.